refresher on interval notation and graphing stuff. So they want us to graph this interval on the number line. It's all the numbers x, so this is one dimension, x, between -1 and 2. So this is like your lower boundary. This is your higher boundary right here. And let's just put them on the number line. -1, 0, 1, 2, 3. Doing a little graphing of this dude on the number line. Tell me about this -1. Included or not included? Included because of that equal to bar. You're very familiar with the open dots and the closed dots. You can use those. On my math lab, though, sometimes they don't have open dots and closed dots. They put the brackets and the parentheses instead. So do you remember which one meant it was included, the brackets or the parentheses? So what they might do, you might see it drawn like this, is they don't put a closed dot above -1, they put a bracket right there instead. I don't care if you use open dots or closed dots, it's up to you. I'm just telling you, when they have those on the screen, you know, it's like, what's this mean? It means that it's included, and the 2, isn't it also included, right? So that's a bracket. And then take a nice thickness and put it on the number line. Your teacher may have showed you to put that above the number line. I'm a person who likes to put it on the number line and put it nice and thick. Cool. Number 2, from 2 to 4, is the 2 included? Nope, and the 4 is not included, so instead of putting the dots, let's put the brackets and parentheses. We need a scale first, obviously, so start at 2, 3, 4, 5, 6. Always finish your scale. There's only 6 little dots there. I have 5, you have 6. Just finish it, you know. Finish what you started is always what I kind of believe in. 2 was not included, so that's a parenthesis. 4, oh, my bad, I didn't write the domain and range. And 4 was not included. And then we go inside of there, and I didn't finish the problem. It says graph each inequality, then write the solution in set builder and interval notation. So let's just start with number 2. Please label what you're doing. Number 2, I want to write this region in set notation. So start with the cool set bracket. It's the set of all x's. That's how you read that. If you've had me before, I've made you say that out loud before. So it's the set of all x's. Then you put this dude right here. Anybody remember what that means? Such that. Set of all x's, such that. And then you just basically rewrite this. And let me tell you how to read it out loud. That is honestly the hardest part and the #1 reason why kids fail college algebra is because they can't read it in the first place. Just gibberish. Set of all x's, such that. Then you always read from the variable first. X is greater than 2 and x is less than 4 is what that really says. Then in interval notation, so we'll do that underneath there, I just put int for interval notation. It's basically like your graph and this comboed together. It went from 2, not included, to 4, not included. Right? This is nothing but parentheses. All right, let's do 3. From -2 to 3, -2, -1, 0, 1, 2. Uh-oh, you had an extra spot though, didn't you? You could make it. Were you able to make it from -2 to 3? Cool. Grapher, -2 does not count, so we put a bracket. 3 does count, so we put a, excuse me, -2 does not count, so we put a parenthesis. 3 does count, so we put a bracket, and then all the junk in between. In set notation, set of all x, such that, and then you just kind of, I write it first and then say it after I write it. Set of all x's such that x is greater than -2 and x is less than or equal to 3. Number 4 only has one boundary, right? These first 3 were double inequalities or compound inequalities where there's a boundary on the left and a boundary on the right. You know, these over here only have one boundary, so we just need to put a 3. I like to put it in the middle, but then finish what I'm doing. 3 does count because of the equal to bar, so I will put a bracket. Since that's a greater than symbol, I'm making the bracket go in this direction, pointing to where my actual ray is going to be. Again, I don't care on your homework quiz next time if you use dots and or open dots and closed dots, or if you use brackets and parentheses. It's up to you, right? If it's right, I will count it right. And if it's wrong, I will count it wrong. X less than 5, I need a 5 in the middle. 6, 7, 4, 3. 5 does not count because there's no equal to bar. And going to the left, to the left, to the left. I didn't do the set and interval notation again, my bad. So let's do set on this guy. Set of all x's such that x is less than 5. Again, the set notation is pretty much given to you in set notation already. You just got to put the set of all x's such that in the set brackets. And then the interval notation, that's where you read the actual drawing that you made. It's like how you always read from left to right. How far to the left did my green arrow go? From negative infinity to 5 not included. We went from negative infinity to 5. Just reading this guy from left to right. It went all the way to negative infinity to 5 not included. All real numbers, got to graph it. Like what should you put down here? Anything you want to. 1, 2, 3, 4, my bad, 0 and negative 1. Got to graph them all. Well, we graph them all. So you fill the whole stinking thing in. And it goes on forever and ever. Let's see how good we are at remembering how to write that in set notation, though. Set of all x such that. That always starts with it. Then, aren't they all the real numbers? So x is an element of, that's like a, kind of looks like an E. Let me draw that again for you. I always make a C and then put a little dude in there. Kind of looks like the letter E. Is an element of the real numbers. What symbol is real numbers? The double bar R. And then close your bracket off. Set of all x such that x is an element of the reals. The more you say it to yourself correctly, the more better you will do. More better, yes. Simple. Next. Nice. All right, so then the old, big old honker definition of a polynomial. This is it. You do not need to have that memorized. You just kind of got to know what a polynomial is. The easiest way to know what a polynomial is to figure out what a polynomial is not. Right? So over here, I have some examples of stuff that is a polynomial. You're free to write that down if you'd like. You know, that's up to you. But I would definitely take some notes on the not polynomial side. So here's the definition of a polynomial. When a simplified polynomial cannot be given, when you have a simplified polynomial, it can't have negative powers of variables. So there's a rule, no negative exponents. It can't have any fractional powers of variables. So the little exponent can't be a fraction. This should be typed out for you. I'm going to put some examples here in a second, and then we'll do that. So no fractional powers of variables, and you can't have any variables in a denominator, and you can't have any variables inside a radical. So if you look through all of these homeboys over here, all of these are good. All the exponents are just normal integers. None of them are negative. There's no fractional powers, etc. So here's some not polynomials. I will give you a second or two to write those down if you choose to. Again, it's your class, it's your notes, right? These are not polynomials, and then we'll discuss why they are not polynomials. What's wrong with him? Why is he not a polynomial? Oh, you can have a fraction. You can totally have a fraction involved. The exponent can't be a fraction, but what's wrong with him? Variable can't be where? So this is the bad guy right there. That is bad. Can't have a variable in the denominator. What's wrong with this guy? This variable is under some sort of radical. That's not good. And then some of you, I know it's the first day of school, but it must be like, well, what if you rewrote it? Remember, you can change a radical to a rational exponent. Like square root of x is the same thing as x to the 1/2 power. Power over root. It's like, what if you did that? Well, that's bad because you can't have a fraction for an exponent either. Like fractional exponents are rational radicals also. So that's our problem here. Would you believe that's no good? Right? And what's wrong with this? It's got a negative exponent. Well, you may remember from way back in the day, it's like, well, doesn't that change houses? Can't that go downstairs to where if you've got a -2, can't that reciprocate and go down here? It's like, yes, it does. But then don't you have variables in the denominator in that case? So can't have it. Those are not polynomials. Then some old school stuff. This is just my little polynomial for an example here. You don't have to write it down. We're going to mow through this and then do some examples. But the degree of a polynomial is like if you're all in one variable, and would you believe we're only using x's, right? There's no y's, no z's, and they're only using x's. The degree is the biggest exponent you see. And in this case, that is 4. Right? So that's a 4th degree polynomial. These are just the other terms involved with it. So the leading term is the guy that's the biggest, well, the one that's got the biggest degree, which is the 5x to the 4th. There are 3 terms here, 1, 2, 3, right? And 5x to the 4th has the biggest degree, so that is the leading term. It might not come first. We'll see that in our example. The leading coefficient, if you remember, coefficient means the number in front of a variable, so the leading coefficient is just a 5. And monomial, binomial, trinomial, those are old school. Monomial has 1 term. Binomial has 2 terms. Trinomial has 3 terms in it. Anything after that, like a 4-term, 5-term, we just call them polynomials. Even though they probably have a name, I don't even know what they are, because we just call them polynomials. So let's do some examples. They say, for all of these, find the constant term, which we didn't talk about, but we will, the leading coefficient, and the degree. See this, homeboy? This is a polynomial. But it is not what's in what's called standard form. Standard form goes from highest degree to lowest degree. Each one of the terms, there is 1, 2, 3, 4 terms are separated by addition, subtraction, or equal signs. So here's those 3 guys. There's 4 terms, 1, 2, 3, 4. Which one of these 4 terms has the biggest exponent on them, the first, the second, the third, or the fourth? This guy. This, if we were to write this in standard form, he would come first. You don't have to write this down. It's 2x to the 4th. Then the next biggest guy is 5x squared. Then isn't the next biggest guy negative 8x? And then isn't the next biggest one 3? Like each one of these terms, I went from highest degree to lowest degree. This is the standard form to write it in. But you might not have to write that down because all they're asking you is who is the leading coefficient? Well, the leading coefficient is the coefficient of the guy that comes first. And you could probably be smart enough to know, oh, well, this one's got to come first, right? Doesn't that have the biggest degree on it? So our leading coefficient is 2. Does that kind of make sense to you? 2 is the coefficient of that guy. And I hit a button, my bad. Then what is the degree of this polynomial? What do you think? It is 4. It is whatever the biggest exponent is. This is a 4th degree polynomial. And the constant term is the term in here that doesn't vary. Doesn't have a variable with it. Variables make things vary. Would you believe this guy here is constantly negative 3? It has no variables with it. So negative 3 is the constant term. So if I was doing this over again and didn't write this out, I always just go grab this polynomial and just go find the dude that's got the biggest one and circle him, making sure I got the sign in front of him right also. And he's the one that's going to answer most of my questions. You and a neighbor, try this one. Find the constant term, the leading coefficient, and the degree in whatever order you want to. I usually do the degree first. How you feel about Wemo? This is our guy that's going to answer all our questions, right? So what's our degree? 6. Leading coefficient? 3. And constant term of? 7. All it takes is practice. We're here knocking the rust off of our brains because it's been a long, long time, right? And feel free to ask any questions that you have, but we're trying to make this short, sweet, and pretty simple on the first day. We okay with that? Let's do a few more things about functions. I believe I have the definition of function written out for you. Is that right? It's typed out for you? So cool. This is the definition of function. We're going to use it to answer some of the questions, so it's there for you. The green thing is the definition. It's some sort of correspondence which every element in the domain maps to exactly one element in the range. Remember domain? X's or Y's. What's domain? X's, right? And the range is the Y's, right? So every element in the domain maps to exactly one element in the range. So we kind of got that taken care of. And now here's a new question that I've added in the past because there's a lot of things on my math lab about it later. There's some things on our test about it later. It says in the following relation, a relation is just a set of ordered pairs like this is. This is just some set of ordered pairs, points on a graph. It says find the domain and range. It's such an easy question that it's hard for most students. They're like, what? You know, like they're thinking negative infinity to positive infinity, that kind of stuff. It's like, nah, man. This is a finite set. It's only 3 points. The domain is all your x's. So we put them in the cool, fancy schmancy set brackets. And would you believe that 1 is in the domain, 6 is in the domain, and 3 is in the domain? That's it. It does not matter what order you put those in. You know, people are like, you have to go from least to greatest. It doesn't matter. You just can't put anybody in there twice, right? Don't put one in the domain twice. It's like if I asked you to go in the hallway, and then I said, okay, now go in the hallway again. You can't do that. You can't be there twice. You're either in the hallway or you're not in the hallway. You're in the domain or you're not in the domain. So the range is all the y's. List all the y's. Don't list anybody twice. And that's 2, 4, 5. Feel okay with that? Again, it's so easy. Most people go, that's it? Yes, that's it. That's your domain and range. Because that was a finite set. Then, here's a nice little chart that I got on your sheet for you of different ways you can see functions and what's not a function. There's relations, tables, and mappings. The relation, again, is a set of ordered pairs. Check it out. 2 different sets here. Mine are colored. Yours are kind of black and white due to the printer. But check out just the green thing. That's all I'm talking about. This is a function. Why? Because every element in the domain, those are the x's, maps to exactly one element in the range. Here's my domain. Meow, meow, meow. If you don't know, I meow a lot. I'm weird. Right? But there's our domain. Right? Here's the secret. The way to just really tell. You see any repeaters? When I highlighted, there's a 1, there's a 2, there's a 3. Was there anybody that repeated itself in that list? So that's a function, right? If the x's don't repeat, that's a function. Same thing down here with the old blue set. The domain is 4, 5, and 6. No repeaters in the domain. But what tricks people on those multiple choice tests when they're kind of not paying attention is they're like, but 4, 4, 4 repeats itself in the range. It doesn't matter about the range. To be a function, it's all about the x's. It's all about the domain. And you can't repeat in the domain. So can you see why this is not a function? Look at your x's. There's a repeater. Who repeats itself? 2. So how will we write that out? We'll do it later. The element 2 in the domain maps to more than one element in the range. 2's partnered up with 6, and 2's partnered up with 4. It doesn't function. It doesn't function. Like if you went to the candy machine or the pop machine and you hit the button 2, a 6 isn't supposed to come out and a 4 isn't supposed to come out. Like it's not functioning properly if that happens. You hit one button, one thing's supposed to come out in a candy machine. The table works the same way. All you're looking at is your x's. Here, this is a function. Look at these. 3, 7, 9, 20. Any repeaters? That's a function. Over here, any repeaters in your domain? Yep, -1 maps with 3, -1 maps with 5. That is not a function because the element -1 in the domain maps to more than one element in the range. And then to see it as a true mapping, that's the cool little bubbles and arrows. The easiest way to see it is when you have a function, everything in the domain, Mr. Orange Bubble right here, has one arrow coming off of it. One arrow, one arrow, one arrow. One arrow coming off of 2, one arrow coming off of 5, one arrow coming off of -1, and one arrow coming off of 7. People are like, well, what about this? You know, it's not about that they're both going to 6. It's about how many arrows come off of 2, 1. How many arrows come off of 3, 1. How many arrows come off of this, 1. How many arrows come off of this? So to be a function in the mapping, every element in the domain has one arrow coming off of it. And can you see why this isn't good, right? Because 8 maps to more than one element in the range. Cool with functions? Then old school. That's when you've just got like a relation, a table, and a mapping. There's another way that we're very familiar with to see if something is a function, but that has to be a graph. That's called the vertical line test. Remember the old vertical line test? But you can only use the vertical line test on a graph. So to refresh your memory, if I could get a line up here, if anywhere you were to draw a line, you don't need to do that for me. I think by now you can tell visually usually if it's going to pass or fail, but you're welcome to draw lines. If I was to draw this vertical line, if it touches the graph, which is the red thing, in one place exactly, that's cool. But if it goes through it more than one time, not a function. So would you believe that this is cool, and then if I do it again, that's cool, and if I do it again, that's cool. I'm trying to find a vertical line to where if I drew it, it would go through there more than one time. And would you believe that is not possible on this graph? So the question is, does this pass the vertical line test? So that means he is a function. So determine what this is a function. We will say yes. And I'm picky. I know a lot of you have never had me before. I'm just one little picky thing. I hate when you say it passes the vertical line test. I need you to say the graph passes the vertical line test, because the only thing that can pass the vertical line test is a graph, so we will say the graph. The graph passes, and you can definitely write VLT, passes the VLT. So if you were to write it passes the VLT on the test, I'd take off a little bit of a point. You know, it's like, it's not what we wanted. It's not what we're talking about. Even though I'm very happy you understand what we're using, the vertical line test, you know, it's like I'm a big stickler on proving stuff with the right lingo. Let's do domain and range also. Unless they ask it to be in what's called set notation, we're going to do everything in interval notation unless they ask. Intervals, the brackets and the parentheses that we like. So we got to understand that there's supposed to be arrows on here. And for those who have never ever seen my straight edge test, I use this a lot when the graphs start getting more and more complicated. Like, you got to understand that this graph right here, because of the arrow, continues to go up forever. But would you also believe it goes to the left forever also? It's continuing to get wider and wider and wider. And domain is x's. And x's go left and right. So if you go as far left as humanly possible, here's -1, -2, -3, -4, -5, as far left as humanly possible, that's called negative infinity. Would this graph run into my straight edge at negative infinity? And because it continues to go left and left and left, the answer is yes. So I say that's a part of the domain. It goes from negative infinity. And then, if you move to the right, the graph is still touching my straight edge, still touching my straight edge, still touching my straight edge, still touching. I go all the way to positive infinity, because that's getting wider and wider and wider. Would you believe that it always touched my straight edge? So that's why it's all reals, from negative infinity to positive infinity. Most people are pretty damn good with domain. It's range that we're just a little shaky on. That was pretty new in Advanced Algebra 2. We haven't had as much practice on all of that. Range is about your y's. We go low to high, right? Your y-axis goes up and down. So I'm going to go as low as humanly possible on this graph, which is called negative infinity. Does this straight edge run into this parabola down here at negative infinity? It does not. It's not touching it. Still not touching, but right here is where it starts touching. And the stupid thing is we have no idea where that is, right? We're going to have to guess. But would you believe it's between -4 and -5 somewhere? So you're just going to have to guess, and that's where the old approximate symbols come in. So it's like, it's about, what do you want to call it, -4 points, I don't care. What do you want? -4.1, -4.2, -4.3, what do you want? -4.2 is fine with me, right? It doesn't matter. What's bad is -4. It's definitely not that. And it's not -5. It has to be somewhere between there, right? So about there to there. Hey, is it included or not included? They're like, there's no dot there. Well, if they wanted it to be an open dot, they would put an open dot there. Do you see an open dot there? So it's a closed dot. So that is included. So go with my straight edge, not touching, started touching right here from -4.2 included. And if I go up, is it still touching? My straight edge still touching the graph? Still touching the graph? Still touching the graph? I'll go all the way up. Would my straight edge still be touching the graph? So it would go to positive infinity. If you did not understand that straight edge test, that's pretty normal if you've never had me before. I will do it over and over and over again. I will continue to do it. Ask questions if you have it. If you can find the domain and range a different way, it's all good. Right? Getting the correct answer is more important than like, I didn't understand what you just said there. But hopefully, when we start doing more of the hyperbolas and the inverse squares and et cetera, the straight edge test will help you. All right, keep rolling. Circle. Is it a function or not? First of all, let's do the vertical line test. Tell your neighbor, what do you think? Pass or fail, the vertical line test? Big fat fail, right? So anywhere, you know, it's like boom. So that answer is no, and we'll say the graph fails the VLT. The graph, boy, this thing is getting old. Fails the VLT. Then domain and range. Again, more guessing McGuessertons going on here. Of where I guess it's pretty close. We'll call this -1. But if I put my straight edge as far left as humanly possible, called negative infinity, no part of that red circle is touching it. Not touching, not touching, not touching. That's it. Starts touching right there. Right? We'll assume that that's at -1. Right? So from -1, we will say it's included also due to the fact that there's no open dots there. And then I keep moving to the right. It's touching it. The straight edge is touching the red circle. The straight edge is touching it. The straight edge is touching it. The straight edge is touching it. And then once you get here and beyond, it's not going to touch it anymore, right? So our domain ends right here at 1, 2, 3, 5, right? 5. When I get really close to the screen, I can't read it very well either, and it's included. Please try the range with a neighbor. Go low to high. This is a -5 right here if you can't see that. So where does it start touching, and where will it stop? Low to high. You can always use a hand. I have straight edges that I can pass out when we really need them. Use your pencil, whatever. Feel good? My bad. Feel good with -6 to 0, both included? Like I said, it's not like we're reinventing the wheel here. You've done all of this kind of stuff before in a class. It's just refreshing the memory and jumping through that hoop to get us that degree. So, all right, and then this is not a continuous function. It's just a bunch of dots. It might not even be a function in the first place. Sorry, I used the word function, but let's see if it is a function, just out of curiosity. Oh, that's part 12, whatever. Let's do it now since I talked about it. Is it a function? It's still a graph, right? It's still a graph. You can use the vertical line test. So if I draw a vertical line, would you believe, right here, I actually didn't go through any part of that function. It's got to go through one of the black dots because I kind of missed. But if I was to do right here, let's pretend it went through that black dot, please. It went through the black dot. How many times did it touch the black dot? Once or more than once? Just once. But right here, if I can get my thing to line up nice, would you believe that that vertical line went through more than one black dot? Right? So does that pass or fail, the vertical line test? Fail. So this is not a function. So no, and you can write the graph, fails the VLT. And then let's find the domain and range. The domain and range, because it's not a continuous graph, you know, back here to where if I was to plot this, it's just like I wouldn't really have to pick up my pencil to draw that graph. It's nice and continuous. This is discrete, a bunch of dots. The domain and range is just your x's and y's. These are just ordered pairs again. So starting with my set, I'm going to put my x values in here. It doesn't matter what order you go in, but I'm going to pick this guy. Would you believe his x value is 1? Right? This is the ordered pair 1, 6, right? So the x value is 1. And this ordered pair right here, 3, 5, its x value is 3. But so is this one. Should I put 3 in the domain again? No, only list it once. So since there's repeaters, that's another way you could say, oh, that's not a function because 3 repeats itself. But you don't list them in there twice. And then there's a 5, and then there's a 7. All right? And then range, you list all the y's. Listing all the y's. So that's 6, boom. A 5, a 2, a 3, and a 4. Whatever order you want to go in. It's just the difficulty is on me making sure they're all in there. How does that feel? Like, do you see that that is a discrete graph to where you're not using like the interval notation, negative infinity to positive infinity stuff. That's kind of new. And then blah, 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 blah. Explain why we said no. This is the easiest explanation right here. The graph didn't pass the VLT. But you could have also said the element 3 in the domain maps to more than one element in the range. That's another way to explain it. But because there was a graph, you could use the VLT. Cool? This question, can I use the VLT? Can I use the vertical line test on this? There is not a graph. Yes, you could make a graph. If you want to go through the trouble to make the graph, then you are allowed to use the vertical line test. But this is not a graph. That is a table. So we're back to the old repeaters game. Is this a function? That's what they ask. What do you think? Nope. So the definite answer is no. But the number one question, I know we're tired, especially those of you that stayed up all night, you know, it's like I know we're tired and it's getting long, but the number one question is, what do you want me to write down again? How do I say this? How do I say it's not a function? I get it when you say 0 repeats itself. You know, it's like at least that's decent. Let's try to do the right language or close to it. Let's say who's the bad guy? What number is the bad guy? So we'll say the element 0 in the domain the element 0 in the domain, maps to more than one element in the range. Maps to more than one element in the range. The element 0 in the domain maps to more than one element in the range.